I want to dedicate this video to a few more examples working with function notation, just to carry us over from our previous lesson. So to start with an example, let's look at the following function. F of x is equal to 2x minus 7. So the first thing I want to do to it is I want to talk about its rule. Okay? So remember, what this notation means is that if x goes into the function as an input, 2x minus 7 comes out. I'm not tired of drawing my little picture yet, so I'm going to draw it. We're getting close to me being a little bit tired of drawing this, but not quite there yet. Right, so we have a function named f. X comes in, the function acts on it, and 2x minus 7 comes out. So in other words, this function doubles its input, doubles the input, and then subtracts 7. Okay, so again, let's try a couple of evaluation examples. So what is f of 3? So more than anything, I want to sort of make clear so we know that the input is 3. And then we want to find the output. So much of the early conversation about functions is that nuance. Do you know whether you are being asked to talk about the input or the output? Once you know, the rest is smooth sailing. So again, this function doubles its input, then subtracts 7. So what you will grow very comfortable to say is that we are plugging 3 in to 2x minus 7. And that becomes 6 minus 7, which is negative 1. By that same token, if I ask you for f of negative 2, right? Like this might feel like a redundant example to you at this point, because by now you might start to feel comfortable. Okay, the input is negative 2. We're supposed to find the output. But what I really want to be working here is I really want to continue to develop this idea that f of x is the output where x is the input. So f of negative 2 is the output that is associated with the input negative 2. Finding that output is not particularly exciting. We just plug in. We do to negative 2 what this function does to its inputs. We multiply it by 2, we subtract 7. That's negative 4 minus 7, which is negative 17. Notice that, I'm going to do this in red, each input only corresponds, so I'll say here corresponds to only one output. So you are never going to have a moment where you say f of 4 is either 2 or 7, right? I made all of those numbers up, but you are never going to have a situation like that where it's ambiguous what the output associated with that input is. That is one of the benefits of the function. It is totally clear what output is associated to what input. All right, let's look at one last question with this function, and then we'll look at another example. What is the value of x for which f of x is equal to 5? Okay, so notice f of x is the output. So we know that the output is 5. And we're asked to find the input. Okay. Well, we have it over here that if you give this function any input, 2 times that input minus 7 comes out. So you can say, well, let's say the input was x and we're solving for x. Well, we know that 2x minus 7 was 5. And now we solve this, and that's pretty quick, right? We add 7 to both sides. We get that 2x is 12. Divide both sides by 2. And you get that x is 6. So what we're saying here is f of 6 is equal to 5. We can double check that in a second. And no other input corresponds to the output 5. This is because this is what's called a linear function. And linear functions are going to have this property that not only is every input going to correspond to exactly one output, but every output also corresponds to only one input. That's called a one-to-one function. I'm not going to worry too much about you guys understanding that right now because we'll talk more about it later. Okay, before we move on to another example, let's just confirm that f of 6 is in fact 5. So f of 6 is 2 times 6 minus 7, which is 12 minus 7, which is in fact 5. Okay, let's do one more example and then that'll be it for this lesson. So let's say that we have the following example. F of x. Actually, you know what? I want to change this for a second. I said that f is the name of a function, and I want to make sure that you understand that f is just like a really, really, really cop-out name. So you can call the function anything you want. And sometimes if the function is actually supposed to designate something like a profit or a cost, we'll name it P or C. But if it's not really designating anything, you'll notice a range of letters also. So for example, let's say we have g of x. And let's say this is a quadratic function. 3x squared plus 2x minus 4. Okay, so I did say it, so I want to write it here. This is a quadratic function. Okay, and again, what this function does is quite complex, actually. An input x is dropped in to our function named g, where g is just a name, and g of x pops out. So if you had to describe in words what this function does, it would be quite a mouthful, right? It squares the input, then it multiplies that by 3, then it doubles the input, adds it to what it just got, and subtracts 4. This would be quite difficult to describe verbally, so the notation is actually really handy in most situations because describing in words what the function does would be really, really complicated. All right, so what is g of 0? Okay. So g of 0, well, again, this is a situation where the input is 0. So we want to find the output. And again, what we're doing here is just going to be a matter of plugging in, right? Since we are taking x and plugging it in here, it'll be 3 times 0 squared plus 2 times 0 minus 4. And 0 times anything is 0, so everything here other than the negative 4 goes away. So g of 0 is negative 4. Okay, let's try another example. What is the value of x for which f of x is negative 10. Okay, so this is kind of an exciting moment, I think. So let's see what happens. So what I'm saying here is that we know the output is negative 10, and we're supposed to find the input. Okay, so we're going to take 3x squared plus 2x minus 4, because that's what our unknown input turns into when it passes through the function. And we're going to set that equal to negative 10. So this is now a quadratic equation. We know how to solve quadratic equations. We set them to 0 first. So we have 3x squared plus 2x plus 6 is equal to 0. So again, this is a quadratic equation that maybe factoring ends up working out, but one of the things we've talked about is, let's look at the discriminant to see if factoring would work or not. So I think it's actually, especially when the quadratic equation has, the quadratic expression has a leading coefficient, I think it's a great way to go. Saves us a lot of heartache, because we need the discriminant anyway if we're going to use the quadratic formula. So let's look at the discriminant. So that's b squared minus 4 times a times c. Oh, 2 squared is 4. 4 times 3 is 12. Times 6 is 72. So the discriminant is negative. And what I hope you all remember from my lesson on quadratic formula is that if the discriminant is negative, it means the quadratic equation has no real solutions. So what that tells us is there is no real value of x for which f of x is negative 10. So the way that we would say that, I'm going to write it in red to be super exciting. Negative 10 is not a possible output for this function. So this is our first experience with something like this. This is our first experience with a situation where something was not a possible output, but it opens Pandora's box, if you will, because it makes us ask the question, so are there times when something isn't a possible input? And how do you know? And so what this leads us up to talking about is the conversation we'll have in our next lesson, which is, if you look at a function, how do you know, or what do you do to be able to say, what are the inputs that it's capable of acting upon, and what outputs is it capable of producing? My little story that I like to tell that I will end this lesson with is, if you walk up to a machine that sells beverages, you shouldn't be surprised that you can't buy a bag of Doritos there. It sells bottles of soda. It doesn't sell bags of chips. By that same token, if you walk up to a machine that doesn't take coins, it only takes bills, you shouldn't be surprised when you can't pay for the thing you're trying to buy for the machine with coins. Functions are machines. It's why I have my little goofy picture that I keep drawing. And just like machines, some functions are quite restrictive with what they will accept as inputs, and very restrictive with what they're capable of producing as outputs. That brings us to the conversation of domain and range, which is going to be our next lesson, but I'll stop this one here. Thank you. Bye.